So today I'm going to give a survey about the famous conjecture about sensitivity versus broad sensitivity. So basically, I will only talk about all the previous no results and discuss some possible way to solve it. So hopefully someone can come up with a proof next time, or maybe even this time.
You're only giving us a week.
Sorry?
You're only giving us a week.
Got a backlog here.
Okay. So first of all, I need to give you the definition of what's a sensitivity and broad sensitivity. They are basically different measures of the complexity of some Boolean functions. So first, f is a Boolean function from 0, 1 to the n to 0, 1. And we define the sensitivity of f at the point x to be the number of coordinates I such that if you look at the value of f at s plus ei, I will tell you what this means in a second. And this is not equal to the value of f at s. And here we just mean if I look at s as a vector in 0, 1, and I take the unique vector with the ith coordinate equals 1 and the other coordinate to be 0. And the sum here is just the sum in z2 to the n. Okay.
So we just change the coordinate.
Yeah, so basically I change the coordinate and see if this changes the value of f. So this is called the local sensitivity of this x. And the sensitivity of the function f is equal to the maximum local sensitivity.
So, for example, input is the expectation of this.
Yeah, if it's the expectation, this is the L infinity node.
Okay.
And I also define the broad sensitivity. So similarly, first I define it locally. This is the maximum number of disjoint subset Si, such that if you change the coordinates in those subsets, then it will change the value of f. So here I did some slightly abused use of this notation because I think of the subset as a 0, 1 vector. I hope everybody can agree with me. Okay. And similarly, we define the global broad sensitivity to be the maximum local sensitivity. Okay. And one thing I like about a nice conjecture is that you can define things in like 5 minutes and then can start stating the conjecture. That never happens in like algebraic geometry or other areas.
Just a question about the block sensitivity. So what you are doing is you consider all different partitions.
I consider first I fix the point x. Then I consider all the different partitions of the coordinates, and they don't have to be consecutive.
Yeah. So and then you take and then for each partition you calculate for how many sets.
Yes.
They fit, and then you take the maximum.
I take the maximum. Yes. It's the same thing, I think. Because you can always extend the disjoint set to the partition. Just by adding.
Sorry, so there, in BSFX, after the such that, is there a for all I?
For every I, yes.
So you need to choose a partition such that everything in the partition changes it. And then you make
No, because all set you count how many sets in the partition.
you count everything.
Yeah, it's like with the singleton. I mean, so sensitivity is the same thing, only your sets are singletons. You try to change it in every coordinate and you count how many times.
Yeah, thanks for the explanation, Abi. This will lead to the fact that the broad sensitivity is always greater than equal to the sensitivity, because you can always take each block to have size exactly 1. Okay. And this conjecture was made by Nissan and Seghetti in 92. they conjecture that these two parameters are polynomially related. So the plot sensitivity is bounded by a polynomial function of the sensitivity. Actually, I think they make an even stronger conjecture, saying that this is quadratic. I saw some paper mentioning this, but I'm not 100% sure. But anyway, proving this will be already nice enough. And the best result known about this is exponential. The plot sensitivity is less than or equal to big O of e to the power of the sensitivity times the square root of sensitivity. And this is by Kenyon and Cooting in 2004. I'll try to give a proof next time, but here I just believe, first I will give a simple proof with the constant here not being e, but maybe 4 or something. And before talking about this, a proof of upper bound, first I need to talk about the best separation. So in other words, we want to find a Boolean function f such that the plot sensitivity is really large and the sensitivity is small. And the best separation we know about this is the plot sensitivity can be as large as the sensitivity square. So it's a quadratic function. And that's basically why they made this conjecture. Any questions so far? Okay.
So of course, the trouble is that it's not the block sensitivity of f at x that you expect to be bounded by the sensitivity of f at x. It should change coordinates with some sort of like majority. It'll be some other point that'll be sensitive.
Yes. Okay. Well, that's the intuition. So first, I will show an example that gives this quadratic bound. It's called the Rubinstein function. So I take a function g on n variables, s1 to sn, and this is equal to 1 if and only if for some there exists I such that si is equal to si plus 1 equals 1, and all the rest are equal to 0. So basically, you look at this n coordinates. If there are two consecutive coordinates equal to 1 and all the other numbers are equal to 0, then this function is equal to 1. Otherwise, it's equal to 0. So the next step is to take a function f on n squared variables. So from s11 to s1n up to sn1 to snn. And this is just equal to the, you take the all, right? All function of all this gi. Then I claim that
One of the rows has its property then.
it's not so obvious, right?
No, I'm saying if one of the rows has its
Oh, yeah.
property, I'm just talking about the definition.
Yes, exactly. So if one of the rows has this property, then it gives 1, otherwise it gives 0.
So the block sensitivity is at least n here, right?
It's at least,
n squared?
yeah, it's obvious that at least n, but I can get n squared. So first of all, the plot sensitivity is at least n squared. So think of this as an n by n transform.
Oh, okay. Because each row you have n different possibilities of being all zeros.
So basically, it will, for example, if you start from 0, 0, 0, start from s when every coordinate is equal to 0, then you change these two coordinates, you get 1. If you change the next two coordinates, you get 1, and so on. So you can partition the chessboard to basically n squared over 2, this kind of 1 by 2 rectangles. So you will get like n squared over 2. And to see the sensitivity is at most constant times n. This requires a little bit more work, but the main idea is, for example, if you look at one row. So you start from some x. So if you want to change the value of x, value of f at this point x, so what you can do is, let's discuss two cases. So if fs is equal to 0, then it means for every row it gives 0. So it means that for every row this cannot happen. And the number of coordinates in each row such that you can make this happen, such that if you change this coordinate, you can make this happen, is at most 2.
Because
Right.
it has to be
Yeah.
zero everywhere else. That's very important.
Oh no, it's actually it's 1 somewhere and 0 everywhere
That's the only way
else.
you
Yeah.
can change it to be a one.
So you can basically change this 0 into 1 and make it 1, or change this 1 to 1. So for every row, there are at most 2 sensitive coordinates. So in total, there are at most 2 times n. So the second case is if f of s is equal to 1. Then it means for some row, there are 2 consecutive things equal to 1, and all the others equal to 0. And all the results coming from the other rows will not affect the value of f. So you can only change things in this row, so that at most n sensitive coordinates. So is this construction clear? Okay. So next I will show a proof. Let me do it on the board. That the plot sensitivity is always bounded by an exponential function of the sensitivity. So to do this, I will let me write this down first. So this is like I don't have the function here. Maybe something like the sensitivity times 4 to the power of the sensitivity. And here there was a lemma by Simon back in the 80s. So he showed that if a Boolean function f depends on all the n variables, then if you look at the sensitivity, it's always greater than the log function of the number of variables. It's a theorem. It's not so trivial, yes. And that's
Define depend.
I will tell you in a second. So let me write this down first. So it's like big O of log n. Yeah, and this is pretty much earlier before they have this conjecture. So it's like not really a lemma that leads to this claim. Okay, so now define what depend means. Depend just means for every coordinate I, there exists some s such that f of s plus ei is not equal
So
to
the influence is
f of s
greater than 0.
if s is non-zero. Yes.
Or you can't write it as f prime of a subset of variables.
So if f doesn't depend on all the n variables, then this is obviously false because you can just take f to be equals s1, and the sensitivity is just equal to 1 and cannot be as large as log n. So
for example, how does this relate to KKL?
There's, in the Nissan Segedi paper, I don't know if you saw it or not. There's a proof of a similar result that uses KKL. But you don't need to. This direct combinatorial argument.
Okay, I was wondering if this follows immediately from KKL or not.
I don't know if immediately.
I'm not sure.
But notice that this is almost tight because the address function.
Yes, you can take the address function. So if you take the address function here, so I guess most of people here know about it, but just repeat the definition. So basically you have 2 to the k plus k variables. So s1, sk, y0 to y2 to the k minus y. This is equal to, so basically you look at the number corresponding to this vector.
So y
and then you write sub s. So the sensitivity of this function is equal to k plus 1. And the reason is because, so every time when you fix a vector, so the only coordinate that might change this value of f is like this k coordinates together with this s vector. So it's at most k plus 1. And now the number of variables is equal to 2 to the k plus k. So this one basically gives you log k, log n. And there's a more complicated example that will give you 1/2 times log n, but I'm not going to talk about this. Okay. So can I go to the proof of this theorem now?
Wait, sorry, why was the sensitivity at most k plus 1? So can you repeat that?
Fix any input. You want to change the value.
Yep.
Well, if you don't touch the address bit and the y coordinate, which is addressed by, you're not going to change the function value by definition.
I agree, but
So what's k plus 1 bit?
So basically all the y coordinates except 1 cannot be sensitive.
no, but I thought so. Sensitivity was, I can adversarially choose what the setting is.
Yeah, so pick your favorite input. And whatever input you want on k plus 2 to the k bit. And now tell me which coordinates you can change to change the function value. I claim that if you don't touch the address bit,
Yep.
and you don't touch the place they address, you cannot change that. Doesn't
Okay.
matter, right? So
Oh,
that's
okay.
just
Yep,
k plus 1.
Okay, now I'll prove this Simon's theorem. So first, before talking about proof, I want to say this will just give you this claim. The reason is because the plot sensitivity is always at most as large as n, which is the number of variables. And this is a monotone increasing function in this variable. So if you plug bs of f here, then you can get this inequality. Okay. So now what I do is I look at, I think of the inputs as the vertices on a n-dimensional hypercube.
Is it proving the claim or Simon's theorem?
The Simon's theorem. I already said in the claim, yeah. The claim just follows using the plot sensitivities at most n. And it's number of variables. Yeah. This, if you have 1/2 here, that's how you get 4. So now what you do is look at the, so I define, so now I think of all the 0, 1 vector as the vertex on the hypercube. Then I define the vertex or vector to be flipped if f of s is not equal to f of s plus ei. So I have to say that since f doesn't depend on any variable, so for every
flipped with respect to I.
with respect to I, yes.
Okay.
So a fixed I for example. So for every I, there always exists a flip vertex because of this dependency. And I call the vertex copied.
Can you write bigger for the camera?
So if f of s is equal to f of s plus ei. And I also call the edges connecting f of s, connecting x and s plus ei for such flip pair to be colorful. So the main idea is we want to use the this kind of conditions to show that there should be lots of colorful edges. And on the other hand, we can use the sensitivity to bound the number of colorful edges. And from there, we can get an estimate of this sensitivity. So
the sensitivity is bound on the number of colorful edges incident
for every vertex.
For every vertex.
Mhm.
Okay.
So now let S equals S of F. Okay. So the first claim is that every flip vertices, every flip vertex is adjacent to at most 2 times S copied vertex. In the hypercube. And why this is true? So let me draw a diagram. So I have a vertex X here.
Wait, I mean,
Mhm.
I gotta. So can you clarify the notation here? So you're saying a vertex is flipped.
Mhm.
I mean, are you saying I flipped? I mean,
I can
the
say
vertex
I.
be both flipped
Now always
You
fix
just
I.
went to
Yeah,
fixed I.
I
Okay,
fix
so
I
fix
first. Yeah.
I.
Mhm.
and then vertices are
This
now
will- this will-
partitioned.
Mhm.
Okay. Into
So
flipped.
basically, I have
Cut it out.
Okay. Fine.
I cut the hypercube into 2 halves and see if these
Fine.
two things has the same color.
Yep.
Mhm.
We'll do separately each of the colors.
And
Yeah,
what is the
then.
second one?
Copied.
Copy.
Copy the color.
Wow.
Mhm. Okay. So here I look at X and S plus EI. And suppose S is adjacent to some copied vertex Y. So the number of Y such that S is adjacent to Y and F of Y is not equal to F of S is bounded by N, bounded by S, right? The reason is because it fixes vector S, and the sensitivity is at most S, so that at most F of S of Y such that F of Y is not equal to F of X.
Just to make sure,
Mhm.
if an edge connects two vertices,
Those
each
the
of them,
Hamming distance is equal to 1.
no,
Mhm.
what I want to ask is if
Mhm.
an edge connects two vertices that have the same value, f has the same value on them, but
Mhm.
Each of them is flipped on another axis. Is the
I don't know.
considered
Now I always
colorful or
now
not?
always do it for only a fixed I.
So
Yeah, mhm.
also the edge
Mhm.
is called colorful.
Oh,
for
you-
this fixed
yes.
But each,
Mhm.
yeah, I mean, each edge already defines which I you're considering.
Yeah.
right?
Mhm.
So the way you should picture this is look at I mean you can use colors, but you can look from X at all it you want an upper bound on the number of flip vertices that
Mhm.
it's adjacent to. So draw them all Y1, Y2, Y3. You want to say that it's impossible that there are many, and the way you are going to argue that there cannot be many is using the ith neighbor of X, because for each one like this, its neighbor, for each Y like this, its neighbor has the same function value, whereas the neighbor of X has a different function value. This will give too high a
Mhm.
sensitivity on the
On
X
X
plus
plus
E.
EI.
Right,
Yeah.
right.
Yes.
Okay.
Mhm. Yeah. So yeah, we already explained the proof. Yeah. So It's-
Why do you get 2S there
2S.
for the claim?
So I get S here, right? Because I only look at the case when F of Y is not equal to F of S. So if F of Y is equal to F of S, then because you know Y is a copied
okay,
vertex,
okay, yeah.
S is a flip vertex. So these
Okay.
two should have different color.
Right.
So F of Y plus EI is equal to F of S plus EI. But then at most S vertices satisfy this condition.
Yep.
So there are at most 2S vertices in total. Yeah.
Yep.
Mhm.
I'm sorry, I didn't get the proof. Either
So I discussed two cases. Either F of Y is equal to F of S, or F of Y is not equal to F of S. So if they are not equal, then because they're at most S such Y, because the sensitivity is at most S.
So let me try. I mean, so we have, X is a flip vertex, right? So we're trying to bound how many copied vertices it's adjacent to. So case one, the copied vertex Y is something which then, has f of Y different than f of S. You count that. That's at most S of them. Because there's a colored.
I'm sorry. If oh, okay.
There's at most S of those because there'd be a colored edge from X to Y. Case two, f of X equals f of Y.
Just a second. If f is different than.
Can I change
Yes.
this just to a colorful language? So put two different colors on X and X plus I, please, just so we see them, right?
Okay.
So blue and yellow, I don't know, red, whatever. Now, on the other hand, every Y neighboring X and its neighbor, its I neighbor, has the same color, either two blues or two reds, right?
So this is one case.
Every copied
By
neighbor.
definition.
Yeah.
Okay, so you're looking at these squares, and each one of these squares has three colors the same and one different. Right?
Because
Well,
X and
because
Y
the
are
Y
the
is
same.
If there were more
Y
than
is copied
2S.
and X is flipped. If Y is copied, then the same color.
So if there are more than 2S of these guys, one of the two
Okay.
either
So
top
and
left or
it's
top
right.
right would be violated
okay,
to be
okay.
colored edges.
Okay.
So basically the
So
number of
it's
such
clever.
edges is at most S, and the number of such edges is also at most S.
It's
So
more
you get
clever than
2S.
it is long.
So what we get from here is if we look at if we call G to be the hypercube restricted on the flip vertices. I also call it GI if you want. I mean, with respect to I, flip vertices. Then this shows you the minimum degree. Delta of GI is greater than or equal to n minus 1 minus 2s, right? Because for every vertex, there are at most s edges connecting this flip vertex to a copy vertex. So if you look at this one, it's the complement, so you get at least n minus 1 minus 2s. And there was a lemma. I hope this is a lemma, no? So G is a induced subgraph. Actually, induced doesn't matter, because when I write down the conclusion, then you will see this of Qn. And the minimum degree is greater than or equal to D. I think a stronger form is known, like the average degree is equal to D. Then the number of vertices in G is at least 2 to the power of D. Okay, it's another theorem. And first I want to show why this is, why you have 2 to the D here. And basically I want to show the tightness. So this is tight if you take a subcube.
Wait,
So what is
no,
D
but
bar?
isn't this? I mean, this is
D
just
bar is the
small set
average degree
expansion. I mean, okay.
of G.
It's hyper. Yeah.
No, you don't need that.
So you can think of it like this. You take a subset of the vertices and look at the subgraph.
Regular? Is it deregular subgraph?
It's not regular. You only need to know the average degree. Yeah. But this one is regular.
I'm sorry, I'm still confused about the previous argument.
Uh-huh.
Suppose that
So-
you have.
Well, we're not in a hurry, so I think we can express
Okay,
everything.
so you know that in every rectangle there are three vertices of the same color. How do you conclude the 2x bound?
You are not allowed more than S.
Yeah.
In any vertical direction, you are not allowed more than S.
Yeah, because
In any vertical,
Yeah,
what's
Mhm.
the vertical direction?
Not the I direction.
vertical is
S
with
plus
respect to
I.
one fixed I.
You are not allowed more than S.
You are not allowed to flip more than S.
You are not allowed to have vertices with a different color.
Okay.
Neither X nor X plus EI are allowed to have more than S neighbors with a different color, because that's a sensitivity bound,
Uh-huh.
and that's it. the fact that they are different than x and equal to y. One of them has to be different.
Yeah, maybe this will help you understand this. So basically in every layer there can be lots of copy vertices or lots of flip vertices. It doesn't have to be like all of them are in the same layer. Okay. So this is typed by QK because you can take the number
QD, you mean?
Q,
Degrees.
QD, okay. So then because the dimension is equal to D, so I have 2 to the D vertices, and every degree is just D. Okay. Actually, I don't know if this is the only type example, but anyway, I'll give a proof of this lemma, and you can see if that follows from the proof.
Well, I mean, there are also subcubes are also typed.
The other subcubes.
Oh, yeah.
And any translation of QD. Okay, just do it. Can I just erase this board? Yep. So proof of theorem 2. So I'll do it by induction. So induction on n. So first of all, I partition the Qn into two n minus 1 dimensional subcubes. Call it V1.
Okay, what are you proving? You're proving the lemma or the theorem?
The lemma.
The lemma, okay.
But we say it's a theorem. So, okay. So V1 and V2
I'm sorry, what is the V of G?
is the vertex set of the hypercube. The 2 to the n vertices.
Oh, it's the okay.
Okay.
So what the lemma says is that the number of vertices of Gi is at least 2 to the D?
Yes, because it's a subgroup. Well, if you take it to be the whole vertex set, then you already get 2 to the n.
The number of I flipped vertices is 2. Yeah.
Yes, exactly. So, so I have such a partition. So I pick this kind of partition carefully, such that G intersect UI, Vi is non-empty. I can always do this. And then I look at the graph G1, which is basically, let me just call this Gi. Then we partition this graph G into two halves, G1 and G2. And we want to count how many edges are in this graph G. Okay. So can I call this vertex set also V1 and I don't like this notation. So Q1 and Q2 is better. These are the hypercube. And V1 and V2 are the vertex set of this G1 and G2.
Q1.
Nobody's taking the.
Oh,
It's the intersection,
I,
yeah.
Yeah, so I, the intersection with Qi.
This is,
Yeah, QI.
yes.
Q1 and Q2 will always be hypercubes, or?
Yeah.
Yeah, both of them are hypercube. I select which direction to use such that to make sure that both of them are non-empty. So from the induction, we know that the number of edges in G1 is at least 2 to the power of the average degree of G1. So I to the power of average degree of G1. So I rewrite this slightly.
Like the vertices of G.
The vertices, yes. Thanks. So just V1. So this is equal to 2 to the number of 2 to the sum of the degrees of the vertices in G1 and divided by the V1. Right? And you need to divide by 2? No, just like this, yeah. So this gives you the sum of the degrees. So here degree is with respect to G1. Okay. It's at most V1 times log base 2 of V1. So basically you get the same thing for V2. And then if you sum them up, this calculates the number of edges inside these two subgraphs. And we know that the number of edges between these two subgraphs is at least, let me see, at least the size of the smaller one, right? It's at, let me see, it's at most, yeah. Yeah, because it's a hypercube, yeah. So now, as you can see, we can start to estimate the total number of edges.
Can you repeat why you have this degree bound?
Because you basically take log of both sides, and you get log of B1 is greater than or equal to the sum of the degree divided by B1, and then multiply both sides by B1. So basically move it to there. Okay.
You're really proving this by induction, but for any set that you have, any graph in the cube, subgraph of the cube that you have, the total degree inside is at most the number of vertices times log the number of vertices. This is what you're proving by induction.
Yeah, so we get estimate on the number of edges inside this part and this part. And the number of edges between them is at most the minimum of the sizes because this is hypercube. And so we get estimate. Let me just finish it here. So the number. Sorry.
Why it's medium? So take one vertex, it will have.
No, because
cutting along the direction, the ith direction.
So both of them are like subcubes. Yeah. Both of them n-1 subcubes. Okay. So now we know the sum of the degrees of the vertex in V is greater than or equal to the sum of less than or equal to V1 times log V1 plus V2 times log V2
Plus the min, right?
plus the min. So
Let's assume it's V1.
yeah, assume it's V1, okay. So assume V1 is less than or equal to V2 plus 2 times V1. So basically what I want to show is that this is bounded by, let me just write here.
You want to get size of V1 plus size of V2 times log
Yes.
the sum.
I want to show this less than or equal to V1 plus V2
Yeah, but he's
times
not
log
counting degrees.
V1 plus V2.
He's counting twice.
Yes. And this is kind of easy, but so, okay, it's calculus, right? So let's assume V2 plus V1 is equal to X. So basically, we want to show that 1 plus S times, it's not so obvious. Okay, can I skip this?
Yeah.
Believe me, it's calculus, yeah.
Calculus, we can see it.
Okay.
It's true.
So now I've already proved the lemma that I erased. So, but if you remember what it is, this will tell you that the number of flip vertices with respect to I is at least 2 to the power of n minus 1 minus 2s. So this gives that the total number of colorful edges, because as Avi mentioned before, that for every edge it can have, well, if it's colorful with respect to I, then it cannot be colorful with respect to j. Right? If every edge it uniquely determines this direction. So this is greater than or equal to the number of directions, which is n times 2 to the power of n minus 1 minus 2s. And on the other hand, if we use the sensitivity, we know that for every vertex, every vertex, the number of colorful edges is at most s. So we get the inequality that n times 2 to the n minus 1 minus s is at most
S times 2 to the n.
times 2 to the n, yes. So this gives you s times 2 to the s minus 1 greater, something like that. Actually, I think I missed half somewhere, yeah. It's a good question.
You have 2s in the exponent. Yeah.
Thanks.
Right, because the degree. Yep.
It's 2s here. Okay. Yeah, I like this proof. Right?
What was this used for? Like,
It was a basic question about boolean functions, so it was not particularly used. It just you had the address function. It was just in the basic understanding of boolean functions. You had the address function, which depends on all coordinates. And, people wanted to know if there's you can have fewer.
Also, there is another. I mean, this particular lemma has another meaning. It's actually some kind of aspect of an expansion bound. If you look at this inequality over there,
wait, which of the simple lemma?
The last the lemma that
The lemma I
the
yeah.
lemma that I just finished.
Yeah, that's yeah. I mean,
So
it's like I think of it like a small set.
it's kind of like isoperimetric inequality. You look at the edges between these two things.
Isoperimetric inequality. This is called the edge isoperimetric inequality of the cube. It was proved by Sergio Hao in the 70s.
Yeah, you get
It
you
was
know log
proved by
of
others.
the 1 over the density.
I've seen it in a proof on in a paper on local decodable codes.
It is used everywhere. Yeah. It's
No,
very basic.
they prove it independently.
Yeah, well, yeah, it was proved probably even independently in the 70s.
Okay.
So how do they give a proof in locally decodable code? Is it also by induction? So
I think they have this proof and another nice entropy proof of
I see.
Alex Samolinsky.
Calculate locally decodable code. Calculate locally decodable code.
Later.
Okay, so in the remaining time of this talk today, so I will talk about the relations of the block sensitivity and many other measures of Boolean function. I need to make a few definitions first.
So are there any natural constraints that one could hope on the Boolean function to make the sensitivity larger than polylogarithmic?
If you assume the Boolean function is monotone, then the sensitivity is equal to the block sensitivity. But that's basically the only thing that I know.
There's also, like graph properties, various
Yeah.
types of symmetry which guarantee high sensitivity.
Yeah, but notice that the Rubinstein function can be made symmetric. If you make it cyclic, then it can be made a transitive function.
Sure, but it's on a polynomial gap, and that's the only kind of relation we get for the symmetry.
That's right. I'm just pointing out that they are transitive, not as transitive as graph functions.
And there's some other results saying that for kind of a family of functions looks like Rubinstein function, the quadratic gap is the best you can hope for. But I don't know what the result is. Yeah, it's probably some undergraduate project. So, okay. So now, for a given Boolean function, I will define the following things. So D of f is the deterministic decision tree complexity. So basically, you have a decision tree. So you're asking what's the minimum depth such that if you input s here, then you can compute f of s in the end. So for every point here, you query the value of xi for some variable si. And then if it's 0, it goes to the left. If it's 1, it goes to the right. Okay. So this is D of f. And C of f is you can call it non-deterministic complexity, but here I like this name as certificate complexity vector of f. So it's basically for every vertex. So let me first define C of f of s. It's the minimum size of certificate. I can call f of s certificate at the point s. And for example, if it's a one certificate, then it means it's a subset of. So a certificate is a subset of coordinates. Such that you assign the values to these variables, and then this uniquely tells you that what's the value of f. So
the certificate gets the CX and then decide what it is, right?
yes. Such that if s and y agree on s, then f of s is equal to f of y. So this is the certificate complexity. And the degree of f is just the degree of the polynomial that represents f. So it's the minimum degree of p such that p is equal to f for every input s.
P is a polynomial over the reals.
Over the reals, yeah. And yes, so if you know the value of f, then this is uniquely determined.
It doesn't matter of 1 minus 1 or 1, 0.
Yeah, so it's
linear transformation, so the degree doesn't.
so you can just write out like p is equal to the sum of like si times 1 minus si. So if yi is equal to 0, y is equal to 1, and f of x, basically something like this. Maybe you need to swap them. And the approximate degree of f now is the minimum degree of a real polynomial that approximates f. P. By approximate, I mean for every s, p of s is the absolute value of p of s minus f of s is at most 1/3.
So in L infinity.
In L infinity, yes. I should.
Define C of F again?
Wait, which one?
C of F?
C of f is the certificate complexity.
What does that mean?
So it's like, so for every x, okay, then there exists a cx such that if y is equal to x on cx, then f of s is equal to f of y.
If you have omniscient power, you could just look at this subset of bits and know the value of it.
Yeah, so
This set is small for that.
yeah, then I take the set that has the minimum size for each x. Then I take the maximum. Yes.
And DFF is
For the decision trees, it's a natural analog for non-determinism. You guess where to look, and you look in a deterministic decision tree, you look where it takes you. Here you can just guess where to look.
And DFF was depth or number of vertices?
Depth.
It's a depth, yeah. Okay. So actually, the reason that we take this to be 1/3 is if you change it to any epsilon, which is between 0 and 1/2, then the approximate degree that they defined are linearly dependent. But I don't know how to solve this. This should be easier.
By amplification.
So how to do this? By
You should take
So what I just talked about is like if you for any epsilon 1.
it's a majority function of f itself 3 times. This will decrease the distance.
Decrease the gap.
One
I
value.
see. Yeah. Okay. So just
And
like.
the degree will grow by factor of 3.
So because of this relation that holds, so we can just take this number to be 1, so it doesn't affect the order of magnitude of this degree function, of this approximate degree. So for the sensitivity versus broad sensitivity conjecture, although the broad sensitivity looks a little bit unnatural, but actually it's like polynomial related to all these parameters. So theorem.
Some of these relations were discovered only because of block sensitivity.
Yeah, I don't know how many of these are well known, so I can mention each of them, and if everybody knows this, then I can just skip it. Okay.
The before norms work only the relationship between
C and D.
and F for the norm.
C and D.
Yeah, that's the result about decision.
I see.
Oh, that's simple? The C, okay.
At least this one is simple.
That's the coolest.
I mean, that's a very surprising one.
No, I mean the easy one. Okay, so let me draw a diagram. Stable. So in this table, so if I put the number, for example, if I put 3 here, and in the bracket 2, this means the broad sensitivity is bounded by the certificate complexity to the power of 3. And the best separation we can get is only 2. Okay. And here I didn't write down the approximate degree. I have some results. I can talk about some results, but because I don't know whether they are tied or not. So, okay, so this thing are trivial, right? It's just 1, 1, 1, 1 because they're equal. It's an easy one. So the next thing I want to show is the broad sensitivity is less than equal to the certificate complexity, less than equal to the deterministic decision tree complexity. It's not symmetric. Yeah, it's very important. So because if f is less than equal to g to square, g is not less than equal to f of square. There's certain kind of sensitivity. Okay. So proof. So, for example, if a Boolean function f has the certificate complexity C of f, then it means there exists S such that there exists a certificate has size C of f. Let me see. Maybe it's better to think of it from the broad sensitivity. Okay. So if so basically for f, there exists blocks S1 to SB S of f that are disjoint and sensitive. So now, if C of f is less than or equal to B of S of f minus 1, then it means that there must be at least one block such that it does not intersect any certificate of this side. So for any C has size Bs of f minus 1, there exists I such that the intersection of Si with Cx is empty. then we can just change this block, and we get a different value. So this C cannot be this CS cannot be the certificate. So now I solve the first inequality. Okay. So the second part is just this is also, so I can skip this part probably. Okay. So it's much easier. I also can add 1 here because of this relation. And actually, you can, so if you look at the OR function, all these 3 parameters are equal to n. This is not so hard. Maybe you're only not familiar with the block sensitivity, then just take the 0 vector. And, well, even the sensitivity is equal to n. So, okay. So 1, 1, 1. This is the easiest one. And let me check which one I want to talk about next because there's so many of them. So, okay.
What paper was this result?
It's probably some folklore result, yeah.
This result is still not interesting because
No, not this result. I'm saying that this table.
It's by many people's result combined together.
just the history. I don't know. You're not.
I'm not
you're
really
not
familiar, yeah.
The connection between this, the definition of block sensitivity and the connection to all these parameters started in a paper of Noam Newton.
This is on the PRAM. Is that right?
Exactly, when he was a student at Berkeley, and what he was interested in is characterizing the complexity of computing Boolean functions by what's called CREW theorem. I mean, at the time it was very fashionable to study very different models of memory access of theorems. That's concurrent read exclusive theorem. And he characterized it, to be exactly for every Boolean function. It's just a logarithm of the block sensitivity of the function. So people knew that it could be slope the sensitivity, but anyway, it was exactly the law. So he defined it for that purpose. And yeah, that started studying the connection between this and other parameters. And some relations are from this paper and some are from the later paper with Mario Segedin. It was the earliest paper.
Okay.
And another thing you're probably not going to talk about, but one of the reasons it's important, especially the degree, the connection to the degree, because you can also look at not just at the deterministic decision tree, but you can look at probabilistic one, and even quantum one.
Oh yeah, even the quantum one.
And it's all polynomial.
So
People use it for quantum law.
So the previous conjecture that block sensitivity and sensitivity of polynomial is related, if that is true, are there any interesting consequences?
Yeah, there are very interesting consequences because sensitivity is very easy to understand, and block sensitivity is very hard to understand. Sensitivity is just you look at the function, you know it, but to know block sensitivity, you have to look at all partitions of the
Right,
integral.
but like for example, relations to depth, lower bounds, or
And degree is degree is also
global.
easy to understand. Degree.
Degree is
It's kind of
I think less easy to understand than sensitivity. I mean, well, it depends what you are given. If I give you the truth table, the sensitivity you can hide, right? I mean, the degree, maybe you need to do some calculation.
That's true.
Scott showed that there is this point there's a computable polynomial time in the truth table given explicitly. But I think that I agree that sensitivity is the simplest to just eyeball.
Is block sensitivity computable in the?
I believe so.
Yeah, because in the truth table side, because it's still exponential, the number of
Oh, okay,
but it's
yeah.
still in the
Okay,
truth
so you can
table
afford
side,
to do.
you
Okay.
can afford to do it, but it's still like,
Mhm.
okay, it's linear time to do the sensitivity, but
Mhm.
something like this.
Linear logarithmic factors.
Yeah, I'm not even sure that you need it, but anyway, this is more costly. Like the block sensitivity, you get quadratic in this terms, but I know sensitivity.
Do we know some functions for which we know block sensitivity but not local sensitivity?
Yeah. Most functions you can think of the sensitivity is easy. Well, I mean symmetric functions are easy. Monotone functions are easy because
There you
they're
go.
the same value. So, but if you invent a function,
Yeah.
I mean, one good challenge is to try to improve this Rubinstein example. Right? Try to find a function which is this. If you just think about it for half an hour, you understand the difference between the simplistic sensitivity and the complex Laplace.
Okay. So the next thing I'm going to show is theorem by Nissan. Such that the certificate complexity is bounded by the square of the block sensitivity. So once again, we assume C of f is equal to C of f of s. So it's achieved at the point x. Now we pick a minimum subset S1 such that f of s plus S1 is not equal to f of s. So this is minimal, which means we cannot take any of its proper subsets such that it still holds. And then we keep doing this process. So when we pick S2, it has to be minimal, and S2 does not intersect the previous Si. So it does not intersect the previous Si, and so on.
So we are picking
A subset of coordinates.
We are
the blocks.
picking blocks.
Yes. So now we can see finally we get some blocks, let's say T of them. And obviously T is at most the block sensitivity of F, right? Because they are disjoint blocks, and such that if you change any block, it will change the value of F. Now if you look at the size of each block, that's actually bounded by S of F. And the reason is because, so if you take any, so for any J in Si, if you look at F of S plus EJ,
And then deleting that
yeah,
coordinate would change it back. Right?
exactly. And this is not equal to, sorry, this is equal to F of S. So it's not equal to F of S plus Si. So if you look at the sensitivity at this point, it's at most the global sensitivity. So Si is bounded by the sensitivity. And why this is useful? Because if you look at the union of Si, then this gives you a certificate.
So it's a stronger theorem. It's the certificate complexity is the most sensitivity times
Yes.
block sensitivity. Okay.
So here you get C of F is bounded by S of F times Bs of F. This is bounded by the square of the block sensitivity. Okay.
So you may have said this, but we got stuck. So the changing anything outside of these sensitive blocks.
Yes, we keep doing this until we get stuck. So, okay. I try to write some number in the table. I will do it later. So, and now we can see this is the best separation. We know it's not quadratic. Best separation is like C of F is equal to the block sensitivity to the power of log base 4 of 5. And the example is basically we find a function E on 6 variables, I believe, such that for every point S, C of F of S is equal to 5, and the block sensitivity of the function the block sensitivity of this function at the point S is equal to 4. And then you do it recursively. So you define Ek to be Ek minus 1 applied on 6 of them, I think. Not 6. 6 to the power of k minus 1 of them. So we start with E0 equals 6 ek minus 1 is okay. It's better, yeah. That's equal to x. So we start with a constant function, and then we recursively apply E. And this will give you
copies of this, right?
6 copies. So this will give like the sensitivity, so the plot sensitivity of Ek is equal to 4 to the k, and the certificate complexity is equal to 5 to the k, which gives this bound. And I think this is really necessary that it's equal to the same number for every x in order to get a proof. Right? You can't just have the certificate complexity is equal to 5 and the plot sensitivity is equal to 4. This will not give you this bound.
So one has to prove that they tensorize, right? The certificates and the.
Yes, that's kind
Are
of.
there any separations, maybe polynomial separations, maybe not quadratic, but maybe something not as good, via this kind of approach between BS and S?
BS and S.
Yeah.
You mean using
You can just take any small example and do it recursively.
Yeah.
I think.
Are
Yeah.
there any such? Do you have people come up with such examples? Is there any hope
Yeah.
that you can get better and better separations just by?
Yes, but
coming
not
up with
better than
small
2.
examples?
Not better than quadratic.
But you can do it using this trick.
Yes.
Okay.
And the example is by showing a picture of 64 vertices. But I don't know what's the nice way to write out this function. So it's a result by Patterson. Patterson, yeah.
It's the same result in which you cut the hypercube in less than. You have a few hyperplanes. It's the same Patterson example where if you want to cut all the edges of the hypercube, you need less than 6 hyperplanes. I think it's the same example.
I see.
So there's a question, basic question about the n-dimensional cube. How many hyperplanes do you need to take so that you can cut all the edges of the hypercube? So there are 2 obvious ways to do it. One is to take all the dimension counts.
Yeah.
That's n. Another is to take all the level counts. So you just according to the weight of the vector, you separate the 0 weight, 1 weight, right?
Okay. Yeah.
That's also n.
Yeah.
And people thought that it's n, obviously it's n. And then Patterson came up with this example, which I think is the same example, where you can take a 6-dimensional cube and you can, it's impossible, right?
Wait, why am I the person?
You're a hyperplane, polytops,
No, but you're
will I
alleging
turn
I'm
to?
the one who's going to say it's impossible.
Yeah, you should, yeah.
There's something that's
I
false
still-
about hypercubes, come to me.
I still think it's impossible.
So you
Anyway,
said
you constructed the,
So it's not known in omega and lower bound.
so
for that,
you're
for
supposed
example,
to cut, all the flipped edges, all the flipped edges.
No, all the edges in the hypercube, right? Or what do you mean flipped edges?
All the,
All the edges in the hypercube.
All that just.
oh, so it's not the same example then, right? Here is the function, it's important.
But what's your what was
I don't
the
know.
Patterson thing that you can
Yeah,
cut
so
the
so now I don't think it's the same example because this is the Boolean function
Mhm.
was there.
But what is the Patterson one?
Yeah, I don't know what's the
There
Patterson.
was a
Tell us.
Patterson.
Uh-huh.
Yeah, so you can cut all the edges of a 6-dimensional cube using 5 hyperplanes. There are 5 hyperplanes.
I see. And omega and lower bound is not known for this?
No, so you can tensorize and you get the same.
Ah.
Yeah, you get n to the log base 6 or 5.
So is that question known? It
What's the
sounds very-
best? No, it's not known. It's not known. Maybe Daniel will be maybe a better person to ask about this.
What's the lower bound again?
No, I think some power of n is more maybe. Not sure. You know,
I don't
you
know.
this?
I don't know this.
Okay,
Yeah.
okay, well, I'll
By the way, so I wanted to ask, so here, for example, it's not just true that C of F is bounded by square block sensitivity, but it is this very particular form of sensitivity times block sensitivity. Do the other sort of bounds have this flavor that, you know, if you took a function which had an exponential gap between sensitivity and block sensitivity, it would, you know, have all of these other parameters, not just polynomially related, but O tilde related with each other. Is that true, or is that not? Do you see what I'm saying?
So I think this is the only one that has this property.
This is the only one that has this property. I see.
Yeah.
Because I guess the polynomials are much worse for some of the other ones, because that's more indirect range, right?
Okay. So what we get here is like 2 log base 4, 5. So the next relation on the study is the D of f and the block sensitivity. And there's a theorem by Bills et al. And there are several other people saying that the deterministic decision tree complexity is bounded by the block sensitivity times Ci of f. So Ci of f is just the maximum over all the I input. So the maximum of the minimal certificate over all f of s equals I. So basically, if we look at the certificate complexity is equal to the maximum of the 1 certificate complexity and the 0 certificate complexity.
Yeah, separating the two sides for the circuit complexity.
Yes. And from here, we can get the corollary saying that D of f is bounded by, so this one is smaller than C of f, so we get this bounded by Bs of f to the power 3, and this is the best bound that we know. So this is.
So by the way, so much weaker bounds are known for the degree and the approximate degree, right? Then
You get 6 or
these are
something,
not
yeah.
so far off from being tight, right?
These are like
There
at
it's
most
6 or something.
6 for the degree and approximate degree. Yeah. This is like 2 or 3 or something.
So
And
maybe you should say that there is an obvious bound of fourth power.
yeah.
So this is that's the new result, but the obvious bound of fourth power follows just.
D of f less than or equal to C of f squared.
Yeah. And in fact, C1 times C0.
C1 times C0.
So you mentioned that this was known even before block sensitivity was defined, right?
So this was known for.
This was
Yeah,
known,
this
but
was
not
known
this.
even before block
Not this.
sensitivity.
Many discovered, but maybe Sipser in 1980 or needed it somehow. Yeah, so that was known, and it's a nice exercise. So this immediately from the previous theorem gives.
It looks almost like, I mean, does it have any similarity to like the AUY thing?
Yeah,
it
AUY
looks
was
the same,
inspired.
right?
Well, AUY is much more
It's inspired by
complicated.
this.
It was inspired by this.
I
So
see.
AUY, so, okay, what does it say? It says that for decision trees, that
If you
that
can't
P
certify
equals
one,
M-
or you can,
P
yeah.
equals NP in decision trees.
Right. And
Right?
AUY is
And
the certification
AUY is for
complexity.
communication complexity, P equals
see.
NP. So,
I would say P equals NP intersect co-NP.
sorry, very good.
Yeah,
NP
that's correct.
intersect quantity equals P. Thanks. That's exactly what I'm saying.
All right, good, I understand that.
Yeah, now you should prove it.
And the lower bound is still BS of
Pretty
X.
similar. I mean, if you know
Yeah,
AUY, it's
that's
similar,
right. You know,
right?
Which one? This one?
No, here,
you're right.
compare D with BS. The lower bound.
You
is
mean the
still,
construction?
no, you get the upper bound, the D of X is less than or equal to.
Oh, the other bound already get here. The block
That is
sensitivity.
still, the better bound is not known.
Sorry, say that again.
So block sensitivity is less than or equal to
Uh-huh.
D of F.
Yes.
Is there a better lower bound known?
No, because if you take the OR function, then it's n.
So that is tight.
It's tight, yeah. They're just equal. Mhm. So before talking about this proof, I want to mention that for this problem, the best best construction that we know is like d of f is equal to the block sensitivity square. And this is basically by taking the and or function. So take Sij, I think. Yeah. And here it will give you the block sensitivity is equal to n, and the decision tree complexity is equal to n squared. And I think it's an interesting open problem to get a better to improve this bound. I believe it should be quadratic.
That's also, provably the best separation between D of F and C of F.
Yes, that's also the.
Absolute success story.
Yeah, that's tight actually.
Say again?
Sorry, what did you say, Andy?
This is also a quadratic separation between C of F and D of F, and that's we know is the best possible.
So another corollary of this theorem is that d of f, or as we mentioned, is less than or equal to square of c of f. If you look at the and or function, then c of f is equal to n. D of f is equal to n squared. Block sensitivity is equal to n. And this is tight. So it's so now I will try to talk about the proof of this result.
What's R of F for this?
The quantum complexity.
What's the randomized?
The randomized decision tree.
You can look either at the expected or you can.
For this example, what is the?
It's also squared, yeah.
For this one, yeah.
So this is not a good example for separation of
No.
R and D. Okay.
Yeah, I actually don't know for quantum complexity what's the best bound and what's the best separation. That's why I didn't put it here. I couldn't. Yeah.
Right.
Grover is one layer.
You can do Grover both layers. It's and or, right?
You can. It's not obvious. It's not obvious. Yeah.
Okay, fair enough.
It's really not obvious.
Okay.
You have the right intuition, and the result for any formula is very. But this was quite recent. By
I don't think so. It was Child and Ben Recker.
yeah,
Oh, this is the span program, or is that
no,
something?
it's
Okay.
yeah, it uses the span program characterization.
So now I'll try to describe a proof of this theorem. So basically, we need to find a decision tree that computes f in depth at most bs of f times the I certificate. And I will describe the following algorithm. So repeat the following process for bs of f runs. So every time we look at the certificate C, so certificate consistent with all the previous ones.
So you mean not just a subset, but actually the values to the subset.
And then I query the value of these variables.
Yeah, when you say
consistent,
you mean that the values are.
The values are also the same, yes. Let me see. Yes.
process for?
I will describe the process here. Then I start to query the variables in C. So here I now look at the, for example, one certificate. So if these variables are consistent with C, here consistent means if it's the same with so the values from this certificate, then you just output 1, right? Because it's a one certificate. So if it's not consistent, otherwise, then we just give value to these variables and keep doing this process. So we repeat this for Bs of f rounds. Then finally, we output the value of fy for any consistent y. Consistent means y has the same coordinate with all the previous variables that have been queried.
I'm not sure what is the process. You keep taking different certificates, or you just look at one certificate?
No, I take a lot of one certificate, but only for the one certificate, not for the other.
So
I take arbitrarily.
So you're saying I equals 1?
yeah.
Yeah, so I'm proving for I equals 1, but it's the same if you change this to 0.
So this, I mean, so this, you've essentially proved it, right? I mean,
So
that terminates because each time you're creating disjoint copies, and there's something
it's not. You have to show that they're disjoint. From this one, it's not very obvious. Okay, but I think I can.
But once they're disjoint, then you have
yes,
a bound of the block sensitivity for
exactly.
how long this goes.
And in every step, you use at most like this. You at most query this number of variables.
So why are they disjoint?
Wait, before disjoint. So what are you doing? You take a certificate and you look at the values, and if you find something different, then it's an input where this subset can flip your.
Exactly. Yep.
Yes.
So if you were to be able to maintain them being disjoint, then you would have a lower bound of the block sensitivity. So that would be why this terminates in at most block sensitivity rounds.
Why on the block sensitivity? I mean, you're not. What does the block sensitivity has to do with this process? I still don't understand. You are not.
You want to make sure.
Different value, you change one bit in the.
You want to make sure that it outputs the right answer in the end.
Okay, so you are just describing a decision.
Yes.
Right, you are just describing a decision. So the decision just keeps taking one certificate and just checks what the value is. Okay. It's only a decision.
Just like here. Then now.
The main thing is to show that it, that it's the correct answer.
Well, I mean, it's the correct answer. That's not the problem to show. What is
No. You want to show at the end. Yeah, that's very important step. Yeah. You want to show that if you still have like y1 and y2, gives two different values. Yeah. Then this block sensitivity is like false.
Stop it. You don't go all the way.
Okay. So basically, I assume. So let's assume. After the block sensitivity, Bs of f steps, it gives we still don't know the right answer. That means there exists y1 and y2, such that f of y1 is equal to 0. For example, f of y2 is equal to 1. And they're all consistent with all the previous variables. And what we can do is we take the set bi. So this is basically the disjoint set we want to get. To be the set of variables. Let me see. Such that ci and y, let's say y1, disagree.
Maybe you can use something other than I, just because you have to prove CI of F. I'm saying like that if you're talking about CI
CI is the certificate you get from the I step.
No, no, it meant I C subscript.
No, this is like maybe BT. This T is like the steps. Yeah.
So the one certificate CT may intersect with the previous ones on places where it's consistent with them. Are you letting CT just be the full certificate, or just the set of things that were queried for the first time at that stage?
Yeah. So it's basically BT is the set of variables that is queried the first time. So those here. And then from here you can show that actually for any s less than or equal to t, b of s is intercept bt is empty, and also this is function f is sensitive on bt, and this gives you that. So if the answer is long after bs sub f steps, then you can take all the c1 from c bs of f together with the certificate the one certificate that corresponding to y2. Let me call it c of f bs of f plus 1. And then you do it, and then you get this bi, and there are block sensitivity plus 1 such blocks, and each of them is like sensitive for f. Then you get a contradiction. So that's the idea. So see what I mean? So we have maybe half an. Okay. So I will talk about Avi's results, so it should be fine. I'm not saying that I'm not saying that it's not important, but I think Avi knows everything, so that's what I mean. Yeah. Okay. So let me first mention what's the best construction we know about it. The separation of
the new results that you're alluding to?
Not really. I'm giving a survey. So.
Oh, okay. Oh, you're talking, okay, older. Okay.
So first I want to mention what's in this bracket. So it's log 3 of 6, log 3 base 3, 6. So basically I need to show you the function which has the block sensitivity, certificate complexity, deterministic tree complexity, decision tree complexity equals to 3 to the k. But the degree is huge. It's equal to 6 to the power of k. So this basically has the same flavor with the function I mentioned somewhere. So this is recursive construction, but we're taking a different function, e. So I let the function e to be the following: s1 to s of 6. It's a Boolean function of 6 variables. And let me write down what the function is, and you will see why this is a Boolean function. It's not so obvious, actually. So the sum of si minus the sum of the pairwise product plus the sum of 10 terms, which is degree 3. So I'll just write them down. 1, 3, 4, 1, 2, 5, 1, 4, 5. But, by the way, this is an example by Kushilevich.
So the pairwise things are like I not equal to j, or I less than
I not equal to j. So we don't have a constant 2 here. Less than. 1, 4, 5. It's probably something comes from design theory. So 2, 3, 5, 1, 2, 6, 1, 3, 6, 2, 4, 6, 3, 5, 6, 4, 5, 6. So by this I'm taking, for example, if I write 1, 3, 4, means in this sum we have this term z1 times s1 times s3 times s4, and so on. And there's no monomial of degree like greater than or equal to 4. And yes, this nice property, first, it's a Boolean function. It's already not very obvious. But the way to check it is like, for example, if we look at how many zeros in xi. So if there's 0, how many ones, for example? How many ones? If there's 0 ones, then this gives you 0, right? If there are one of them, then it's 1 minus 0 plus 0, it gives you 1. If there are two of them, again, these terms of degree 3 do not contribute. So it gives you basically 2 choose 1 minus 2 choose 2, which is equal to 1. And if there's 3 of them, you get 3 choose 1 minus 3 choose 2 plus. So here, if these 3 variables which are non-zero appears in this sum, then it is 1, otherwise it's 0, right? So there are two cases. So this is like either 1 or 0 because 3 is equal to 3. And the nice thing about this design is that if you look at any quadruple, it has exactly 2 triples from this set. So for example, if you look at 1, 2, 3, 4, then 1, 3, 4 is here, 2, 3, 4 is here, but the other two are not in this set. So which means, for example, so for example, if there are 4 variables are not equal to 0, you get 4 choose 1. From here, minus 4 choose 2 plus. So here is basically 1/2 times 4 choose 3, or you can just say 2. So this is equal to 4 minus 6 plus 2, this is 0. And if you do the same thing for 5, you get 5 choose 1 minus 5 choose 2 plus 1/2 times 5 choose 3 is equal to 5, 5, 5, 0. And for 6, you get 1. So now I already kind of putting a lot of effort to get this is a Boolean function. But as soon as we get this, it becomes really nice. So
any 5 tuple has exactly half of it.
5, yeah, half. You can get this from the quadruple by double counting. I mean, if every quadruple has density 1/2, then this 5 tuple has density also 1/2. Right? It's an exercise. So. So let's see. I almost forget what I need to prove. So I need to show that from this. So okay, first of all, this example has block sensitivity. So even for sensitivity is equal to 6. So this implies that the block sensitivity, the certificate complexity, and the decision tree complexity are all equal to 6, which is the number of variables. And why sensitivity is 6? Because you look at the all 0 vector, then if you change one coordinate, you get 1. And now the degree of f is equal to 3. So if you do it recursively, so ek is equal to e of ek minus 1. And there are 6 of them. Then the degree is equal to 3 to the power of k. And you can show that the sensitivity is just 6 to the power of k. So all the rest are equal to 6 to the power of k. Or you can just simply get it from here because you also look at the all 0 vector. Okay. So this gives the best separation. And the bound I want to prove is kind of interesting. I'm not sure how much time I have, so maybe I can prove 1 or 2 of them. Let me see which proof.
By the way, at the end of the day, is this whole table gonna? Are there any cells that we don't know anything, like the bottom?
For this table, we know everything. Well, it depends on where you.
All of these are polynomially related.
Yeah,
Oh, that's
everything is
they're all
polynomial.
right. Okay, yeah.
And also for the table, I show you every number you get from here is like the best bound we can get, and this is the best separation we can get. Yeah. But it really depends on what you mean by do we know everything, because these two are not equal, right?
Okay.
So, Also, I will also mention why this degree is like polynomial related. The approximate degree is polynomial related to the others. So,
And if S is not polynomially related to BS, like if there's an exponential example separating them,
S and BS,
if they're not polynomially related, would it imply some?
then you
something that-
disprove this conjecture.
Sorry?
You disprove this sensitivity. And,
But I mean,
yeah,
like, would that have implications to?
to other.
Would that cause some separations people don't expect or something?
Well, but nothing else is related to sensitivity.
That's, yeah, I don't know. I only know about this
Right.
this problem itself.
So we have this clique.
Mhm.
And the question is sensitivity part of the clique?
Yeah, I understand. I'm saying if it's not, does that imply? Like for example, in complexity classes, right? If you can show something, it would imply something collapses, something other. I'm asking like, why should S and BS be polynomially related?
I agree with the spirit of the question. I mean, I'm not sure there are any consequences.
There are
right?
no-
Yeah,
there
I
are no
don't know.
consequences.
I'm not sure there are consequences either way.
Mm-hmm. So I'm either proving it or disproving it. Yeah.
Andy, do you know any consequences?
No, I mean, I've looked at most of this literature. I haven't seen anything like that. I think it would be surprising, and it's inherently an interesting question, but I don't think it would have.
The motivation of the question is just purely intrinsic, that sensitivity seems so much more natural than, than block sensitivity at first, and
Right.
yet that's the one.
Yeah, I think it's kind of like a problem that mathematicians are interested in. They define some parameters and then start studying the relations, and they don't really care what's the consequence. Yeah. As long as the problem is short and elegant.
You
Yeah.
know you're on video, right?
I could stop.
So, okay. I'll try to talk about one more proof, but I have to pick which one that is less interesting. It's often easier to decide which one is more interesting. Okay, so this is the result showing that the certificate complexity is bounded by, so first of all, it's bounded by the decision tree complexity. So I want to show that decision tree complexity is bounded by the block sensitivity times the degree. So this will imply that both of them, the certificate complexity and the decision tree complexity, they are both smaller than the degree to the power of 3.
Why?
No, let me see. Because of block sensitivity. So I didn't.
Corollary of just this theorem plus what
No, I
we
think you missed one.
I missed one thing that I think is more interesting, so I decided to leave it for next time. But okay, I mentioned it here. So there's another theorem saying that the block sensitivity is bounded by the square of the degree. And the proof is quite interesting, so talk about it next time.
Is this the Nissan Sazegedi?
Yes. This one used the Markov's inequality, but not the one in probability. Okay. So, yeah, that's about we can
Wait,
get.
What are you saying? It's the what inequality?
The proof is the Markov's inequality.
Markov's little brother.
Yeah, I think it's a little brother. But actually, the version I need to use is proved by Markov himself. Yeah. The version I need to use is proved by the Markov. Yeah. But his little brother generalized.
It
Yeah.
is, about the derivative being at most the degree squared.
Yes. So basically, it's.
I don't know what's.
I still don't know how to prove it. So if you have a polynomial p of 0, 1, and you look at the L infinity norm of the the derivative is bounded by the degree of p squared times the L infinity norm of p.
Yeah.
Does anybody know an easier proof? There are some proof using variation.
That's a pretty well-known and
Yes.
basic. Okay.
But I don't even know a proof for this case. And there's a generalization. This is by the Markov that everybody knows about. And there's a generalization by his brother. So another Markov, I don't remember the first name. So, okay. So if you look at the case derivative, then the L infinity norm is bounded by, let me call this degree to be D. So this is bounded by
E choose,
something like
but
that.
this follows from induction by.
Not really. Right? No, I don't think so. Let me write it down, and I don't think it's so obvious. Square.
Do you know what this follows from Jackson's theorem?
Which theorem? Is it?
Jackson's theorem
I
talks
don't know
about,
what So what's the theorem?
it says that if you have a function,
Mm-hmm.
it says if you have a function
Mhm.
that doesn't deviate too much on small intervals of size, let's say 1 over k
Mhm.
interval, then there exists a good degree k polynomial approximating it in L infinity.
I see. Yeah, I
And it
understand.
also has a version with derivatives,
Mm-hmm.
which is why
Yeah, I'm not sure whether it follows. Yeah. Mm-hmm. So it's a 2k minus 1. So since it has this 3 here, so from this form I can't see how to get it from the induction. Maybe.
Well, first of all, you need a p infinity bound on the other side. But,
Mm-hmm. Yeah, and I also want to mention that this is tight for the Chebyshev function. Chebyshev polynomial. So basically we have T0 of x equals 1, T1 of s equals x, Tn plus 1 of x equals 2s times Tn of s minus Tn minus 1 of x. And this will give you the tight bound in both cases, I believe. So for example, let me check for T2, okay. So T2 is equal to 2s squared minus 1. Okay, so by the way, these are, let me see. You can assume these are on minus 1, 1. That doesn't matter.
The relationship between this and the theorem.
That's a long story. That's why I didn't want to talk about it this time, because I have only. Okay, but it's good to mention this Markov inequality first. Then next time I can remind this again, and then we can go to the proof. Okay. So if you look at T2, then the L infinity norm of this polynomial is equal to 1, I believe. And if you look at the derivative, it's equal to 4x. So the maximum is achieved when s equals 1, so it gives 4. And this is like the degree square. You can do the same thing for the other, but I don't know the proof of this Markov inequality. Maybe I should check the literatures to see if there's any proof, and maybe I can present it next time. And also tell you how this implies that the Bloch sensitivity is bounded by a quadratic function of the degree. I will talk about this thing first. It's much easier to solve. And if you combine these two results, it will give you that the certificate complexity and the differential complexity is bounded by degree to the power of 3. And both are the best best upper bound we know. And also this 2 is the best that we know. So think of that. So imagine that there exists a 2 in that table. Okay. So so basically I want to show that there exists a decision tree. Compute f in the plot sensitivity times the degree steps. So we'll describe the following algorithm. So first we give a ordering to all the 2 to the n monomials. So basically all the monomial S1, S1 to Sn up to S, the product of Si. Okay, so just any ordering. And then, so we start with take any mass monomial. By mass monomial, I mean a monomial in F with the maximum degree. Well, F can be like non-homogeneous, so basically I take the monomial with the highest degree. Okay. And then we query the variables of this monomial. So in every, so this is like one step. And so in this step, we need at most, we need to query at most the degree of F
So then,
variables.
Okay, so then in each max monomial, you're going to say that there's.
Yeah, it's very similar to that proof. Yeah. So or you can say in other words, so you can, now you already know the value of these variables, then you can assign the values to them, and then you get a new function f prime, for example, as equal to f, when you assign this something 1, 0 to these variables, and then you repeat this process for f prime. And it's easy to show that you need to use at most the number of steps you need to use is at most the plot sensitivity. That's how we get this bound. And I'm still owing you the proof of the plot sensitivity is bounded by the square of the degree. So maybe I can talk about it next time and finish now. So because it takes like maybe 20, 25 minutes to explain it, and I don't have much stuff left for next time. Okay, thank you.
So each of these max monomials at the stage when it's chosen is a sensitive block for the input that consists of
Yes.
ones just on that and zeros elsewhere.
Exactly. Yeah. And the render and new ordering is just for picking this monomial. Okay, any other question? So basically next time I will show that the plot sensitivity is bounded by the square of the degree, and it's all for some constant, and it's also bounded by the some constant times the square of the approximate degree. And this already gives you the best bound between the degree and the approximate degree, which is like the degree is less than or equal to, so let's see, the degree is less than or equal to, okay, I still need to finish these things. Okay, so after I finish the whole table, you'll get the degree is less than it's bounded by the deterministic decision tree complexity, bounded by, let me see, the block sensitivity to the power of 3 is bounded by the approximate degree to the power of 6, basically. Okay, that's it for today. Thank you.